Hello and welcome. In this video, I'm going to talk about the Lagrange interpolation. Lagrange interpolation is a method used to construct a polynomial that passes through a desired set of discrete data points. This method is normally expressed as follows. We consider a function f of x, a function which we can call f of x, and suppose that this function is prescribed at n points. So this function is given by a certain set of data. We have x1 and the corresponding value of the function, x2 and the corresponding value of the function, which is x2, x3 and the corresponding value of the function, which is x3, and like that all the way up to xn and the corresponding value of the function, which we can call fn, so that we have n data points. Now, for such a function, a function which is described by such discrete data points can be approximated by another polynomial, which we are going to call y of x, which is a polynomial of degree at most n, a degree at most n minus 1, in this case n minus 1, not n. So this function is in such a way that the value of y at each of the node points xk is equals to the value of the function at the node points, so that the function y passes through the same points as f. So this function agrees with the function f at each of the node points. Now, this function can be expressed as y of x is equals to the sum from k is equals to 1 to n, lk, a function of x, multiplied by fk, where fk is the value of the function when x is equals to xk. K here takes the integer values from 1, 2, 3, 4, and so on up to n. So that fk we have f1, f2, f3, or all the way up to fn, as we have in the above table. Now, fk here, we call them the fundamental polynomials. They are given by x minus x1, x minus x2, x minus x3, all the way up to x minus xk minus 1, x minus xk plus 1, all the way up to x minus xn, divided by xk minus x1, xk minus x2, and this goes to xk minus xk minus 1. Then we have xk minus xk plus 1, all the way up to xk minus xn. Basically, we can write this in a simplified notation as the product of the quantity x minus xi divided by xk minus xi. So I takes the values from 1 to n, so that xi, when I is 1, we shall have in the numerator x minus x1, x minus x2 all the way up to x minus xn. But we say that there is one quantity which is not there, one factor which we can write x minus xk. That one is not included. So it means that y will not take the same value as k. So we can write here I is not equals to k. And then we can say k starts from 0, from 1 to 2 to 3, all the way up to n. So that when k is 1, then xi cannot assume a value of 1. So I will start from 2. And when k is 2, then I will start from 1, but it will not take the values 2, so it will jump to 3, and so on. So we call this the fundamental polynomials. And then the y can now be expressed in this form. So if we are given any value, if we are given a value of x, then we can compute the fundamental polynomials and substitute back here to get the value of y. So maybe we can have an example. If you are given a set of data, say you are given x and the corresponding value of the function, the value of x is 3.87, then 13.7, then 20.24, and the associated values of y, we have minus 18.41. These are the values of the function. 159.967, then 255.067. Then see that this quantity here will be our x1, this one will be x2, and this will be x3. Then the associated values here, we can call them f1, f2, and this one is f3. So that in this case, we can compute, we can say when k is 1 here for the fundamental polynomials, when k is 1, I will not take the value of 1, so x minus x1 will not appear. We'll start with x minus x2, then x minus x3. So we can write L1 will be x minus x2, x minus x3 divided by x1 minus x2, x1 minus x3, and this will give us x minus 13.7, then x minus 20.24, and then the denominator we have x1, which is 3.87 minus 13.7 multiplied by 3.87, again x1 minus 20.24. See that we can compute this, the denominator, then in the numerator we'll have the x. If a value of x is given, then we can compute the value of L1. Then L2 will be, now k is 2, so I cannot take the value of 2, so we can have x minus x1, then x minus x3, and the denominator will be x2 minus x1, x2 minus x3, and we can substitute the values. So we have x minus 3.87, x minus 20.24, which is x3. Then the denominator we have x2, which is 13.7, 13.7 minus 3.87 multiplying 13.7 minus 20.24. And finally, L3 will be x minus x1, x minus x2. Notice that this time I will not take the value of 3. So the denominator we have x minus x1, x3 minus x1, sorry, then x3 minus x2. And we can substitute the values, so we get x minus x1, which is 3.87, multiplying x minus x2, which is 13.7, and the denominator will be x3, which is 20.24, minus 3.87. Sorry, we have 3.87 multiplying 20.24 minus 13.7. And then we can write y y of x. Y of x as L1 times F1 plus L2 times F2 plus L3 times F3. If you are given a value of x, if you are given, for example, x is equals to, say, a value like 12.39, a value like 12.39, for example, then we can compute y at 12.39. We can compute that value of y. What is the value of y? We just need to substitute the values of x here, 12.39, and here. So we compute the fundamental polynomials. The values of f are known. f1, f2, and f3 are known. So once the values of the fundamental polynomials are determined, then we simply substitute the values here and compute the value of y. So basically, this is not difficult to work out when you have such 3 points as we have here, because this one is a quadratic interpolation, basically, because we have x times x, which is x squared. There are only 2 quantities here to multiply, and 2 in the denominator. And that one is not difficult to do. But as the number of points increases, you may find that trying to find the fundamental polynomials may be quite a task. It's quite a lot of work. So what we can do is to write a Matlab program that can do this. A Matlab script that can do this work. The first thing we do is to read the data. So we write the input, which we can call xk, the values of x, which were the values given there, 3.87, we have 13.7, we have 20.24, then the values of the function, which were 15.346, 159.967, and 255.067. Notice that we use the square brackets. Use the square bracket, not the round ones. and the semicolons here is to constrain the output. Then we can have the value of x at which interpolation is required, 12.39. Again, I can put the semicolon there. Then we use the loop. First, we need to know how many data points do we have, or what will be the value of k. So I write the length of x, k, so that n will just be equals to the number of entries here in xk. So now I can write the loop for j is equals to 1 to n. I have xk here, but notice that when computing the fundamental polynomials as we had up here, the fundamental polynomials, I needed xk, which is the set of data that is provided, but I also need xi, and notice that xi is just the same values as xk, only that there is one value that we need to remove from that set, xk. K takes from the values from 1 to n. I will also take 1 to n, but I cannot assume the same value as k, because we don't have xk minus xk. So the value at one value will need to remove it from that set. So we shall write that xi is equals to xk, but again say that xij is empty. Xi at j, so that when j is 1, xi1 will be, there is no entry, there will be no entry there. When j goes to 2, xi at 2 will be deleted, and so on. So then I can now write the fundamental polynomials. I'll call them Lj. So this one is the product. I have x minus xi. I'll use the dot, then the division, then xk at j minus xi. We can constrain the output, then we add. Then we compute y. Y is equals to L dot times f. And then we can print the output using the fprintf function. So I write y at 12.39, but because I can change that value, I'll put the placeholder 0.2f is equals to, then I'll put the placeholder to put the output here, which is y. So 0. I'll use 6 decimal places. Then we have, sorry, there is no comma, no need to have a comma there. So then I have the escape character. So I have the value x and y. Those are the values that I want to place here, these two placeholders. So in this case, we have the set of data. The first step is to read the data for xk, f, and the x, the value at which interpolation is required. Then we need to know how many entries do we have, n. n is equals to the length of k. This will just count the number of entries. We can use the length of xk or the length of f. This is just the same. So then we put the loop f for j is equals to 1 up to n. N is now this value that we have obtained here. Xi will be equals to xk. Then we need to remove one of the entries from xi, and then we compute the fundamental polynomials. Then from there we compute y, and then we print the output. We can do this in Matlab. We can do this in Matlab. So we have the data entry here, first line, the second line, and we don't have this. There were 3 points. Then we have said that we write the n, which is equals to length of x, k. I want to constrain the output, so I'll put the semicolon. So here I'll now write for j is equals to 1 to n. Then xi is equals to xk. And then we remove one of the entries there, so that I should not be equals to k. And then we can print, we compute the fundamental polynomials, and then compute y, and print the output. So I'll run this one. When I run this one, something is not correct here. Let me just clear off everything. And run again. So I'll get the output as 140.810545, which is the value of y when x is 12.39. So if I want to get the value of y at any other point, I'll just change the value of x here. Maybe I want to get the value at 11.2. If I want the value at 11.2, I'll learn, and I'll get the value at 11.2 is that. If I want the value at 5.32, I'll change the value of x and learn, and I'll get the value of y at that point. So basically, this is how we use the Matlab to do the interpolation using the Lagrange interpolating polynomials. Notice that this one, because we have just indicated n here, the length of xk, even if we increase the number of points here and the associated number of points here, if we have more data, you can just enter here, and then the value of the program will determine the value of n. So we don't have to change anything here. So basically, you can do more practice on this by using different sets of data and learn, and then see what you get. So thank you for this, for watching. In the next one, I'll look at the Newton's method. Thank you.